All right, here goes. First, just some basics about probability in general. We're going to have some terminology definitions today that'll be important for us. And one of those is the sample space. And the sample space for any event is all of the possible outcomes, everything that could possibly happen. A real basic example would be if we had a single six-sided die. And on a single six-sided die, our sample space would be 1, 2, 3, 4, 5, and 6. That's it. That's everything that could happen if you rolled a single six-sided die. That's it. That's our sample space. That's all the possible outcomes. For a lot of the problems we work on, we won't necessarily need to list out the sample space, but a lot of times it could come in handy for us to list out the sample space. And so just sort of understand if you're being asked for a sample space, or if I happen to mention that, list out the sample space here, that's going to be helpful, then you'll know exactly what we're talking about. We're just listing out everything that could possibly happen. There are two different types of probability. The first of those is theoretical probability. It's what should happen. If we have a fair coin with heads on one side and tails on the other, we would expect half of our flips to come up heads and half of our flips to come up tails. That's what should happen. We're not actually going to flip the coin 1,000 times if we're doing theoretical probability. Instead, we're just going to say, well, based on what I'm seeing here on this coin, theoretically, I expect the probability to be whatever it may be. Theoretical probability is calculated. This is going to be the probability that we are most interested in over the next couple of weeks as we talk about probability, theoretical probability. We will do some experimental, but primarily we're going to be focused on theoretical. Now, I just mentioned theoretical or experimental. What is that? Experimental probability is what we get after the result of some sort of experiment or activity. An example of this one that I like is, what if we were to flip a thumbtack, and what's the probability it lands pointing straight up? Now, I have no idea how I would even go about calculating that probability, because I can't even guess what the probability is that it would land pointing straight up. So instead of using theoretical probability to calculate this, I would just do an experiment. Maybe I take 100 thumbtacks and I throw them up in the air and I let them land, and then I count how many landed pointing straight up. That's how we find experimental probability, is actually by doing something, by performing some sort of experiment or activity to get that probability. Experimental probability has a couple of other names. It's also known as relative frequency of an event, or the empirical probability. I tend to use experimental most of the time when I'm talking about this, but you might see the others come up in other books, other classes, something like that. So we have theoretical and experimental, two different types of probability. The majority of the problems that we work on are going to be here in the theoretical area. Any questions on that one? All right, the single most important thing about probability is how we find it. And probability is equal to successes over outcomes. If there's only one thing you remember today, Thursday, going forward the next week or two, probability is successes over outcomes. Kind of, maybe write this one on your mirror so that you see it every single day, all the time, that probability is successes over outcomes. Essentially, what we're doing when we find probability is we want to know how many different possible things are there, how many outcomes are there, and how many of those are successes. It's very important for us to talk about the word successes a little bit here. A success does not necessarily mean something good. It doesn't necessarily mean that we win something. Essentially, a success is, did the thing happen that we were looking for? That's what we would call a success. So it's not about whether this is a good thing or a bad thing, whether I win or lose. What a success is did the thing that I'm looking for happen? If it did, then we call it a success. And when we're looking for probability, we're looking for successes over outcomes. Clearly, you can see that probability can be written as a fraction. That'll be very common for us. You're also going to be asked to write probabilities as a decimal. If you're asked to write it as a decimal, you just take one more step and do successes divided by outcomes, and you'll get a decimal that will represent the probability. This is the most important thing about probability. Now let's take a look at how it works. A single six-sided die is rolled. Find the probability of getting a 3. So I'm just going to ask you some questions here on this first one. The probability of getting a 3. Well, we know that the most important thing about probability is that it is successes over outcomes. In this particular experiment, I am rolling a single six-sided die. How many outcomes do I have? You just type this in there for me. I know it's not a hard question, but I'm really hammering home the idea of successes and outcomes. Perfect, Lorraine, Nicole, that's right. We have 6 outcomes. And then the probability of getting a 3. This notation over here is the probability of getting that particular outcome. So that's what that notation means. The probability of getting a 3. So a success here would be getting a 3. If I roll a single six-sided die, how many ways are there on there for me to get a 3? How many successes do I have? Perfect. Lorraine and Nicole, awesome. I have 1 success. I have 6 outcomes. So the probability of rolling a 3 is 1/6. At its core, at its heart, that is probability. We are going to look at much more advanced questions than this as we go forward, but the heart of probability is right there. How many outcomes are there? How many successes are there? And probability is successes over outcomes. Just as a sort of a quick little opportunity, that bottom one down there, I'm going to make a poll for. And it says, what is the probability of getting an odd number? And we're still rolling a single six-sided die. And then my question to you here is, what is the probability of getting an odd number? Reinforcing the idea that probability is successes over outcomes. A little bit of a review, I guess, of what's an odd number anyway, because there are odds and there are evens. Anything that is an even number is divisible by 2. If it's not divisible by 2, then it's odd. That's another way of thinking about those terms. That should go back to 122 for you. We'll go another 15 seconds on this and then talk about it together. Okay, let's see where we are on this one. Okay, not unanimous, but very strong agreement. That's good news. Let's take a look at this one. So, what is the probability of getting an odd number? And so, remembering that probability is successes over outcomes. And on this single six-sided die, we're going to have 6 outcomes. And then the successes are whenever we get an odd number. off the top of your head, you may be, well, that's 1, 3, and 5. That's easy enough. You may want to list out the sample space here and say, okay, here's the sample space. That's an odd number, that's an odd number, that's an odd number. So those are all 3 ways to get an odd number. So I have 3 different successes here and 6 outcomes. So the probability is 3 out of 6. One thing you may be thinking, perfectly reasonable to think it is, could we write that as 1/2? Yes, absolutely you can. Do you have to? No, you don't. When we're talking about probability, if you want to reduce the fractions, you can. If you've been sort of trained somewhere along the line that anytime you can, you better reduce that fraction, I understand, I get it, but you don't have to. When we're talking about probability, and here's my justification for that, here's the reason for that. When you see 3/6, you know exactly how many successes and how many outcomes there are. If that gets reduced to 1/2, the probability hasn't changed. You could still, this is the exact same value as this one. They have the exact same value. There's no difference between them. This is just as correct as 3/6 is. But in some ways, it doesn't give us the same amount of information. All it tells us is the probability is 1/2. Over here, I can see the number of successes and the number of outcomes, and that can have some value. So because of that, you do not have to reduce fractions while we're studying probability unless you want to. If you want to, make sure you do it correctly. If you reduce this to 1/3, now you're wrong. So it's totally up to you whether or not you want to reduce them, but if you do, make sure you do it correctly. And yeah, Nicole, both answers would be correct on a quiz or an exam. Yeah, so both answers would be listed as correct answers. 3/6 would be listed as correct, 1/2 would be listed as correct, so you'd get credit for either one. Great question. Any questions there before we try a couple more dice rolling questions? Okay. A single 6-sided die is rolled. Find the probability of getting a number that is less than 15. I won't do a poll for this. I'm just going to let you tell me, what's the probability of getting a number that's less than 15 when I roll a single 6-sided die? Don't overthink it. Trust yourself. And again, probability is still successes over outcomes. That hasn't changed. So with that in mind, what is the probability of getting a number less than 15 if I roll a single 6-sided die? Your instinct is correct here, so don't second guess yourself. Well, there's definitely something about 6 going on, but I need successes over outcomes. So I like Lorraine's answer very much, but if y'all could write that as a fraction for me, I'd appreciate it. All right, Karina, very good. Excellent. 6/6. Natalie, 6/6. So we have 6 outcomes on that dice. 1, 2, 3, 4, 5, 6. How many of them are less than 15? Well, all 6 of them are. So I have 6 successes and 6 outcomes. Lorraine's answer of 1 here is correct. So is Karina and Natalie. But what we're dealing with here is if I roll a single 6-sided die, this is always going to happen. Every single time I do that, I'm going to get a number less than 15. Similar, but a little bit different than that. Okay, I'm going to roll that single 6-sided die. What's the probability when I roll that single 6-sided die? What's the probability of getting 15? What is the probability that I'm going to get 15 when I roll it? And again, trust your instincts. You're 100% correct. Don't overthink it. Perfect, Lorraine. Nicely done. Stephanie, good. Genesis, well, Genesis, careful with that denominator there. Because we do have outcomes. So here we still have 6 different outcomes. I could get 1, 2, 3, 4, 5, 6. What? How many successes do I have? When I roll that dice, how many are there? There are 15. Well, none of them. So I have 0 out of 6. You might be thinking, these questions are crazy. What's the point of these? You would agree with me, I hope, that this is never going to happen. If I roll a 6-sided die, I'm never going to get a 15. Okay, so there is a method to the madness of these 2 questions, and it is this. The probability of getting a number less than 15, the probability of something that's always going to happen every single time is 1. The probability of getting a 15 on that dice, the probability of something that is never going to happen is 0. Where this leads us to is the fact that all probabilities are between 0 and 1. All probabilities are between 0 and 1. Something that can never happen has a probability of 0. Something that will happen every single time has a probability of 1. So all of our probabilities are between 0 and 1. How this is useful for you is if you're ever doing a probability question and you come up with a negative answer, it can't be right. If you're doing a probability question and you come up with an answer of 5, it can't be right because all probabilities are between 0 and 1. Anything bigger than 1 can't be right. Now, this may be the number of successes you have, but that's not the probability. The probability has to be between 0 and 1. And so it's kind of a nice little self-check that's built into every probability question that if I get anything bigger than 1, I need to go back to the drawing board and rethink this thing. If you're thinking, well, that's not very many possibilities for different probabilities to even occur. Well, yes and no, right? Because we're looking at a 6-sided die, but I don't know. I could have a probability that's 34 out of 1,025. Oh, okay. There's an infinite number of probabilities between 0 and 1 because there's an infinite number of fractions that are between 0 and 1. So, okay, I get it now. But the thing to remember here is all probabilities are between 0 and 1. So anything bigger than 1 can't be a correct answer for a probability question. Any questions about that concept? Fantastic. Dice and cards make for wonderful tools for probability questions. If you're very familiar with dice and cards, that's great. If you're not, we're going to talk about both of those things a little bit today so that you are at least more familiar now than you were when class started. If we roll a pair of dice, and this is fun for me because I get to lean back into something that we did last week. If I roll a pair of dice, so I roll 2 6-sided dice, and I'm just going to ask you this quickly. How many different possibilities are there on the first dice? How many different things could possibly happen? This isn't a probability question. This is how many different things could happen on that first die? How many different outcomes are possible on that first die? 6. Perfect, Genesis. Thank you. And how many different possibilities are there on the second die? 6. Thank you. All of you. Great. 6. And so according to the fundamental principle of counting that we did a fantastic job on last week, if I have 6 different possibilities on the first dice and 6 different possibilities on the second dice, and I multiply those together, there must be 36 different possible outcomes. And that's what you see over here in this chart is all 36 outcomes if we were to roll a pair of dice. You might be thinking, I, I don't know, you can only get 2 through 12 if you roll a pair of dice. Well, what you've done there is you've added the numbers up. And that is something that's very commonly done, but don't think about that quite yet. We'll get there. Forget about adding them up. Just what could happen. There are 6 things on the first dice, 6 things on the second dice, so there's 36 things altogether, and they're shown right here in this picture. And one of the things that I want to make sure to point out to you here is this. When you look at this picture and you see there's a 1 with a 2 and a 2 with the 1. And I want to talk about that for a minute because you might not recognize those as being different immediately. But if you look at those 2 different colored dice, what I've got there to make these different from each other is that on the red dice, this has a 1 and the green dice has a 2. And then when we look at this outcome over here, now the red dice has a 2 and the green dice has a 1. And so those are different from each other. Sure, I have a 1 and a 2, but they're different because what was on the dice changed. I went from a 1 to a 2 on the red and a 2 to a 1 on the green. So they're different from each other. And it's not because the 2 is on the left and the 1 is on the right. I could just as easily write this way with the 2 on the right and the 1 on the left. And even still looking at these, what's on the dice has changed. The red one went from a 1 to a 2. The green one went from a 2 to a 1. So they're different from each other. It's important for me that I know that you recognize those as different from each other. And if you don't, it's perfectly fine for you to ask about it. This is something that students sometimes struggle with. So it's perfectly okay for us to hash it out if we need to. Usually the next question then is, okay, well, what about this right here? You've got a 3 with a 3. How come that's not on there twice? And it's an excellent question. If you look at that, what we have is a 3 on the red dice and a 3 on the green dice. If I were to rearrange those and put the green dice over here and put the red dice over here, well, yeah, they've changed positions on the table. I've moved the dice around, but what's on the dice has not changed. These are the same as each other. And so that's why that is only in the chart one time. It's not about what's on the left and what's on the right. It's did the thing that's on the dice change? And if it did, then we call it a different outcome because it is. If you're comfortable with that, that's awesome. If not, please let me know so we can talk about it a little bit more. Okay, fantastic. Let me clean up some of these scribbles I've got here. And we'll go forward and answer some questions. Here's a poll for you. 2 dice are rolled. What is the probability that the sum of the faces is 10? So our question here is, what is the probability that the sum of the faces is 10? I'm going to set up a poll for this one, and I'm going to go back to that picture so you can see them. What we're after here is, what is the probability that the sum of the faces is 10? I'm going to set up a poll for this one. Remember, the most important thing about probability is it's successes over outcomes. It's kind of nice having this picture. Essentially, what we've got here is we've got our sample space all written out for us. So keeping in mind that probability is successes over outcomes, we're looking for the probability here. We'll go another 30 seconds and then talk through this one together. All right, let's see what we've got for this one. Okay, strong agreement, but definitely some disagreement. All right, so let's take a look here. It could be an issue of counting. Um, as we look at this one, we're after probability, which means we're after successes over outcomes. We already know because of the fundamental principle of counting, or by looking at this chart, or by the idea that we've kind of talked about having 36 outcomes here, that we're going to have 36 outcomes. So that's good. And all the answers that came in on the poll identified the 36 outcomes. So that's terrific. Now it's about identifying the successes correctly. And a success is any outcome that results in a sum of 10. And so, I don't know, depending on how comfortable you are with dice and how familiar you are with games, Monopoly, Sorry, there's all kinds of different games, craps, if you will. But you might start over here and go, well, the sum of that is 2, so that's no good. 3, 4, okay, maybe I don't need to be counting over there. Maybe I'll count over here where the larger numbers are, and there's a 12, that's no good. 11, hey, here's a 10. A 6 with a 4 would make a 10. And then that's 9, 8, 7, 11. Hey, here's a 10. 5 with 5 would make 10. And then 9, 8, 7. And then 4 with 6 would make a 10. And then that's 9, 8, 7. 9, 8, 7. Okay, that's it. That's it. These three outcomes right here have a sum of 10. And so I have 3 successes out of my 36 outcomes. So the probability of getting a 10 is 3 out of 36. If you wanted to reduce that to 1/12, you could, but you don't have to. Are there any questions about what we did there to find the probability of getting a sum of 10? 36 outcomes, we identified our successes. There were 3 of them, so the probability was 3 out of 36. Okay. I want to look at one more dice question, and we'll do this one together from the start. 2 dice are rolled. What is the probability that the sum of the faces is less than 5? So now what we're after is the probability that the sum is less than 5. Probability question. So we know we're going to be doing successes over outcomes. It's just making sure we're careful when we identify our successes that have a sum that is less than 5. We'll go back to our picture. So this time we want the probability that the sum is less than 5. And again, we're looking for successes over outcomes. We know we have 36 outcomes. I'll give you a second. I'm not going to do a poll or anything like that. And I'll type this one, or I'll write this one. You don't have to type it. But so we're looking for outcomes that have a sum less than 5. Now, one thing I do want to mention about this one, if you're practicing it there, is if the sum is equal to 5, that's no good because we need the sum to be less than 5. So let's see here. As I go and I look, well, those have a sum of 2, 3, 4, 5. That's no good. And I go over to the other one. That's 3, 4, 5. That's no good. 4, 5. That's no good. Okay. So I believe I've got all of my successes. I've got 1, 2, 3, 4, 5, 6 of them. I have 6 successes and 36 outcomes. So the probability of getting a sum less than 5 is 6 out of 36. If you wanted to reduce that to 1/6, you could, but you don't have to. Totally optional. Let me know if you have any questions about that before we move away from dice and into something else that I want to talk about with you. All right. The words and or. In day-to-day language, there's definitely a difference between and or. When we talk probability, these words have very specific and important meanings. First, the word and. If we see and in a question, in order for something to be a success, both things must happen. And you're going to see examples of this very soon, I promise. So if it says and, if we're going to count it as a success, both things have to happen. This may lead back to your study of Venn diagrams in 122 when we had intersect. Because if in order to be in the intersection, that was when we had one thing and another thing. And so this is very much like intersect when we did Venn diagrams and set theory in 122. Okay, then the word or. The word or, to be a success, at least one of the things must happen. It could be this one or it could be that one. It doesn't have to be both. In mathematics, it's important to identify the type of or that we mean. Anybody who might be deep into English would understand that there are 2 different types of or. There is exclusive or, which is when you go to a restaurant and they say, would you like soup or salad? You only get to pick one. You can't have both. You can have soup, you can have salad, you can't have both. You can't just say yes to that question, as much as it would be great. It's exclusive or. That means you get one or the other, not both. There is also inclusive or, which would be like if you were going to a hot dog vendor and they said, you want ketchup or mustard? Well, you could say, I want ketchup, I want mustard, I want both. Inclusive or, it's okay to have both. When we talk about the word or in mathematics, we are talking about inclusive or. So when we say to be a success, at least one of the things must happen, that means it could be the first thing, it could be the second thing. If it happens to be both, that's just fine. We're going to count that too. We group these all together. This is very much like union from your set theory back in Math 122. I'm not going to ask you intersection and union questions. It's just, if you did really well with that, if you like the logic associated with that, then it applies here also. And Both things have to happen to be a success, or at least one of the things has to happen to be a success. This is going to be really valuable for us when we start looking at probabilities involving a deck of cards, and that's what's coming up next. Some of you, maybe many of you, are really comfortable with a deck of cards, but just in case some of you are not, we're going to kind of talk through the anatomy of a deck of cards, because you're going to see probability questions related to a deck of cards, and I don't want it to be a totally foreign idea for you. So there's a deck of cards. First thing to take note is there are 52 cards total, and they're divided into 4 what are called suits. We have one suit up here that is hearts. Underneath that, we have diamonds. As we move further down the page, the next one is clubs, commonly referred to when you're teaching kids as puppy feet. I don't know if y'all did that with yours, but I did that with mine. And then finally at the bottom, we have spades. We have hearts, diamonds, clubs, and spades. And what you can see here in the picture is the hearts and diamonds are red cards. That's half of the deck are red cards. And then the clubs and the spades are black cards. And that's half of the deck are black cards. Now let's talk about the makeup of each suit. When we look at each suit, we'll just look at the hearts up here at the top. What I've got is an ace, which is like a 1, and then 2, 3, 4, 5, 6, 7, 8, 9, 10. And then after we get to 10, then we have these other cards over here that are the jack, the queen, and the king. So you can see that there are 13 different cards within each suit. They run from ace all the way to king, and there are 13 of them. One thing I want to say about jack, queen, and king, because they have pictures of people on them, those are often referred to as face cards. If you see anything involving face cards, that's what it means. It's talking about the jack, the queen, and the king. So there's sort of the makeup of a deck of cards. We have 52 cards total, which means there are 13 in each suit. There are 13 hearts, 13 diamonds, 13 clubs, 13 spades to make our 52 cards in the deck. For suits, half the cards are red, half the cards are black, and the jack, queen, and king are called face cards. With that sort of anatomy of a deck of cards in mind, we're going to look at answering questions that involve a deck of cards. One card is drawn from a standard deck. Find the probability of getting a 7. So our first question here is, what is the probability of getting a 7? And I'm not going to set up a poll for this one, but I will give you a chance to let me know what the probability is. Now remember, the most important thing about probability is that regardless of how simple or how complicated the question is, probability is successes over outcomes. So let's see, I need how many? Very good, Lorraine, Natalie, excellent. I was gonna go bit by bit, but y'all did great. Okay. There are 52 outcomes because I'm going to get one of the cards out of this deck. There are 52 of them. And now what I need to know is how many successes are there? We'll go back and take a look. We want to know the probability of getting a 7. So let's see here. I have a 7 of hearts, 7 of diamonds, 7 of clubs, 7 of spades. There are 4 different 7s in the deck. So I have 4 successes out of my 52 outcomes. So the probability of getting a 7 is 4 out of 52. You could reduce it to 1 out of 13, You could reduce it to 2 out of 26 or 1 out of 13 if you want to, or you can leave it right here as 4 out of 52. Let me know if you have any questions on that before we go down and look at that next one. Terrific. The next one, what's the probability of getting a card that is not a diamond? Here again, we're looking for successes over outcomes. I'm picking one card from the deck, so I know right away I've got 52 outcomes. Now I have to figure out how many successes there are. How many successes are there, meaning how many cards are there in the deck that are not diamonds? And you can type it as I was going to say, type it as the probability is the good way to go. Thanks, Natalie. Stephanie, excellent. And if everybody else is right there with them, it's perfectly fine for you to type it too. That's a whole bunch of nodding heads around the room for me to look at. Perfect, Karina. 39. And let's see, where do we come up with that number? Well, not a diamond. Well, that would be these 13 hearts, these 13 clubs, and these 13 spades. And when we add all those together, that's 39 cards. Oops. That's 39 cards that are not diamonds. So I have 39 successes out of 52 outcomes. So the probability of getting something that's not a diamond is 39 out of 52. You could reduce that, but you don't have to. Let's try a couple others. We spent some time talking about and or. Here goes. One card is drawn from a standard deck. Find the probability of getting a card that is a 7 and a heart. Please keep in mind here the meaning of the word and. In order for me to have a success, it has to be a 7 and it has to be a heart. Both of those conditions have to be met in order for it to be a success. Take a second, think that through. Again, I'm not going to do a poll for this because I kind of want it to be more of a discussion. Very good, Lorraine. Excellent. I'm looking for all the cards in the deck that are a 7 and a heart. Well, I'm drawing one card from a standard deck, so I know there's 52 outcomes. That much we get almost for free. Now coming up with the successes. That's a little more challenging. And I need a card. I need all the cards in that deck that are a 7 and a heart. So we'll go back and we'll take a look. Okay, this one's a 7 and a heart. That's a 7, but it's not a heart. That's a 7, not a heart. That's a 7, not a heart. These are all hearts, but they're not 7s. Okay, so there's only one card in this whole deck that is a 7 and a heart. The only card in the whole deck that meets those conditions is this one right here, the 7 of hearts. That's it. So I only have one success out of my 52 outcomes. So the probability of getting a card that's a 7 and a heart is 1 out of 52. Please let me know if you have any questions about that. Okay. We're down below, we're looking at almost the exact same question. The probability is the same, the 7's the same, the A is the same, the heart is the same. The only thing that's changed is instead of a 7 and a heart, now I want the probability of getting a 7 or a heart. I'm still picking one card from the deck, so there's still just 52 outcomes. But when I go to look for my successes now, what I'm looking for is a 7 or a heart. What that means is anything that's a 7, that's a success. Anything that's a heart, that's a success. So what am I going to end up with for the probability here? And be careful. Excellent. You guys are doing a great job with this one already. It's perfect. We've got 16 out of 15, 52. We've got 17 out of 52. So let's think about this for a minute. You go, very good, Nicole. You're totally dialed in. So just off the surface, right? Well, I've got 4 7s. I've got 13 hearts. So there's 17 successes, right? Let's go look at our deck. So if I go back and I look at my deck and I say, All right. So I want to count all these sevens. Now I want to count all the hearts. So I'm going to go count all the hearts. Now so far I've got 4, and there's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. The problem with just saying, well, there's 4 sevens and 13 hearts is what we do if we do that is exactly what Nicole mentioned. We've counted the 7 of hearts twice, and we don't want to do that. We want to be careful not to count that same card twice. So you could do this 2 ways. You could say there are 4 sevens, and then there are 12 other hearts to get our 16 successes. Or if you prefer, you could say there are 13 hearts and then 3 other sevens to get to that 16 different successes. So in this particular case, anything that's a 7 is a success. Anything that's a heart is a success. We want to be careful not to count anything twice. We don't want to count the 7 of heart twice. We don't want to count it once. We definitely count it. The fact that it's both things is good. We keep it. We're going to count it, but we don't want to count it twice. And so we end up with 16 successes out of 52 outcomes. Please let me know if you have any questions about how we got to 16 out of 52 for our probability there. The last thing I want to mention here before we leave this page is this. This question says, find the probability of a 7 and a heart. And the answer was 1 out of 52. This question says, find the probability of a 7 or a heart. And the answer is 16 out of 52. Very similar questions with very different answers. The word and the word or have very different meanings, and it's important for you to recognize and understand that difference and then apply it correctly when you look for your successes. If you have questions about it, please don't hesitate to ask. It's very common to be a little confused about this the first time you see it. So don't be shy. If you have questions, we can talk about it. If it makes perfect sense, then that's great. That's great. Okay, fantastic. One more type of probability we're going to look at today, and that's multiple events. So far, we've looked at rolling a single 6-sided die. We looked at rolling a pair of dice, and we looked at drawing a card from a deck. Now we're going to do 2 different things. We're going to flip a coin and roll a die. Let's see. My first question to you about this is, how many outcomes are there? If I flip a coin and roll a die, and I'm considering this like, one sample space at the end of it, how many outcomes will there be in my sample space? And as a hint, this is all about the fundamental principle of counting. Almost, Lorraine. You got the 2 numbers right, but what does the fundamental principle of counting tell us to do with them? Ah, fantastic. Very good. All right. So I am going to flip that coin that has 2 different possibilities, heads or tails. And then I'm going to roll that 6-sided die, which has 6 different possibilities. 1, 2, 3, 4, 5, 6. Fundamental principle of counting says, how many possibilities are there for each stage of the problem? And then multiply those together. So we're going to have 12 different outcomes here. Now, when there are only 12 outcomes and we're being asked to find a probability, you might be able to do this without listing the sample space, but I don't know if I could. And there's only 12 of them. So I'm just going to go ahead and list out the 12 different outcomes here and then use that sample space to answer whatever probability question gets thrown my way. So I flip a coin and I roll a die. So I could get heads and a 1, heads and a 2, heads with a 3, heads with a 4, heads with a 5, heads with a 6. And then I could get tails with a 1, tails with a 2, tails with a 3, tails with a 4, tails with a 5, tails with a 6. And I can be confident that I have all the possible outcomes in my sample space because the fundamental principle of accounting told me there should be 12. I have 12. So I know I have them all. With that in mind, there are 12 different things that could possibly happen. They're in that box. And I want to know what is the probability of getting heads and an odd number. So in order to be a success here, it's got to have heads on the coin and it's got to have an odd number. Both of those things have to happen. We know we have 12 outcomes. We're pretty confident in that. Think about how many successes there would be, and then let me know the probability of getting heads and an odd number. Very good, Lorraine. Nicole, thank you very much. That's awesome. And I'm hoping Karima's coming in with the same thing. If not, we can talk about it. It's important to post some things like the fact that there were 16 out of 52 and 17 out of 52 last time made it so that we could made it really easy for us to discuss that. So even if the answer that you're about to type in, if you're not that confident, you're not sure that it's right, it's okay to answer it. It just gives us a chance to talk about it if it's not the right thing. So don't be shy. It's okay to be wrong. We wound up with 3 out of 12 here, and let's see if that's the thing. So we need heads and an odd number. Well, that's heads and an odd number. That has heads, but it's an even number, so that's no good. Heads and an odd number, heads and an even, heads and an odd, heads and an even, and then these don't have heads, so they're out for sure. So I wind up with 3 successes and 12 outcomes. So the probability is 3 out of 12. If you wanted to reduce this to 1/4, you could, but you don't have to. If you were asked to write this as a decimal, you would just do 3 divided by 12, and that's 0.25. So as a decimal, that probability would be 0.25 or 0.25. Let's try another one like this. Coin is flipped and a 6-sided die is rolled. Find the probability of getting tails or an odd number. I'll set up a poll for this one. We'll go another 30 seconds and then talk about this one. All right, let's see where we are. Okay, strong agreement, but very interesting. It's rare for us to be spread across all the answers. Okay, let's take a look here. So what we're going to do is we're going to flip a coin and roll a six-sided die. And so when we do that, we're going to have, let's see, 2 and 6, so 12 outcomes. And we can make a list of those. It's only 12, so it's not that many. If it was 48 outcomes, I wouldn't want to list them. But with 12, okay, we'll list them. And I go heads with a 1, heads with a 2, heads with a 3, heads with a 4, heads with a 5, heads with a 6. Tails with a 1, tails with a 2, tails with a 3, tails with a 4, tails with a 5, and tails with a 6. All right, there's my sample space. That's all 12 outcomes. So I know the probability I'm looking for here is going to have 12 as a denominator because there's 12 different outcomes. So that much we know for sure. All right, now I need to figure out how many successes we have. And successes in this case are tails or an odd number. Really important word is or, because what that means is any of these outcomes that has at least one of those two things happen. If it's tails, it's a success. If it has an odd number, it's a success. So with that in mind, we'll go count up our successes. So let's see, if it's tails, it's a success. So I can go ahead and count all of these right away. Because all I need, if it has tails, it's a success. I'm counting it. And then if it has an odd number, I'm going to count it. So that would be, let's see, this has an odd number, so that's good enough. This doesn't have tails, doesn't have odd, that's no good. This one doesn't have tails, but it does have an odd number. Doesn't have tails, doesn't have an odd. Doesn't have tails, but it does have an odd number. That's good enough. And then this one doesn't have tails, doesn't have an odd number. The thing we need to be careful about, we don't want to count anything twice, but you'll notice I didn't go through and I'm actually going to work through this again. I'm going to go back and count those up again. If I had done this the other way, if I had gone through first by looking at my odd numbers, and I said odd number, odd number, odd number, odd number, odd number, odd number, and then I go through and I count up my tails. What I have to be careful about is I don't want to count this twice. So, but I want to make sure I count these because those have tails and that's enough to be counted. And so now I've identified all my successes. And altogether I have 1, 2, 3, 4, 5, 6, 7, 8, 9 successes. I have 9 successes and 12 outcomes. So my probability here of getting tails or an odd number is 9 out of 12. You could reduce that to 3/4 if you want to. If you were asked to write this as a decimal, you would just do 9 divided by 12 and end up with 0.75. And that would be the decimal version of this answer. Either way, we want to make sure we're careful about identifying those outcomes. Again, the word and, extremely important, means in order to be a success, you have to have both of these things. You have to have heads and an odd number. And that only happened in those 3 outcomes right there. With or, you can have at least one. Tails, we're counting you. Odds, we're counting you. Everybody, we're counting you. All the tails, all the odds, we're counting everybody. And that's how we wind up with 9 different successes here. Oh, fantastic, Natalie. That's great. That's very good. It's always good when that happens. Always good when that happens.